us do animations in class, and has helped greatly in getting the books put together too that you get for free. So anytime you have questions about the animations, he'd be the first one to go to. I know something about them. He built the animations from things that I did on a Macintosh using Xcode, and the problem with Macintosh is they're expensive, so always we had students that couldn't afford the things. That's all done now. Everything we make runs on a browser, so everybody can take part in the animation revolution. The thing that I should point out is that this particular class is really key to critical thinking, and we're interested in making sure that the way you think helps. Right now in this country and also in others, research is done what I call beehives. There are groups of students and postdocs and professors that get together and make a large group. And most of the papers that come out today, grab this one right here, your seat of honor. The thing that happens with that is that all of the papers have maybe a dozen authors. When I grew up, one author most of the time, maybe two, collaborated with somebody. But now it's maybe as many as 100, and some of the high energy work. So what you need to do when you're in a group like that is figure out how you can stand out, how you can finesse something first, how you can be clever. In other words, how you can really use critical thinking and get outside of what everybody else is doing. Because one of the disadvantages of Beehive are the groupthink. And so this is a class that's trying to show alternative ways to do things, and we'll do that today. We're going to do most of our work with a ruler and compass today. That I mean really primitive geometry. This goes back before Euclid. This is 600 BC, not 300 BC. This is Thales geometry that we're going to use today to introduce classical mechanics and its fundamental axioms. So we very much play with Occam's razor, and we'll explain what that is shortly here. Before we get too far though, if there is a second semester of this class, it would use one of my best friends' book. Rick Heller has really figured out ways to use classical mechanics to do quantum mechanics. And he's become famous amongst particularly chemical physicists. So I hope sometime during this year he may visit, and we'll have him for the professor that day. He's really good at many things. Also, if you're interested, after classes, bull sessions are in place. And one of the things I want to point out to you is the degrees that you guys have now already or are getting, BS, MS, and PhD. You should be aware that this is old-fashioned. BS stands for bullshit. MS stands for more of the same. PhD, piled higher and deeper. We're trying to do better than that. Okay, that is important. But be aware that PhD has philosophy. Philosophy is the sort of the bedrock of the liberal arts and sciences. Logic is number one of the 7 liberal arts. So that's something that really has to be brought out and made clear as the powerhouse behind all of this stuff that we do. So what I would like to do today is just do the simplest type of mechanics that you could possibly do. And I would recommend this if you're, some of you, I guess probably at least half of this class will someday be teaching a class somewhere. And here's some ammunition that as far as I can tell, no one else has. So you're getting something here that you couldn't get, as far as I can tell, anywhere else in the world. And that's a good thing, right? Maybe, if you can understand it and make use of it. So let's get started, and I will move slides around on these other projectors, but this will be the primary one right here. Here is what we're going to do first. And I'll go ahead and advance the slide on that one and on that one. It's there to this point. It's actually going a step ahead there. But the basic idea that we're doing here is imagining a situation that could have happened to any of us on the way to school, and that is a collision between two vehicles. Here we're imagining that a SUV, and I want to make sure that all of you that are not American born know what SUV stands for. Does anybody need me to tell you sports utility vehicle? Okay. And VW, that's the other member of this little experiment we're doing here. You know what that stands for? Make sure the people's car, Volkswagen. Okay. This poor little Volkswagen is about to get hit by a SUV driver who is busy texting. Okay. And it's a no-no, right? Take your eye off the road, you're asking for trouble. But anyway, this is just a collision between two vehicles that were going, well, this guy's putting along at 10 miles an hour, this one is going 60 miles an hour. So we're going to do, by geometry, we're going to calculate the result of this collision. Two extremes. One, elastic, and this wouldn't happen at 60 miles an hour, but maybe at 60 feet per minute, a parking lot collision, okay, could very well be nearly perfectly elastic. The other extreme is what would probably happen on the highway, totally inelastic, where they become one piece of metal. Okay, now, just to make absolutely clear that you know how we will do the geometry, that is how we will display it, let me just go ahead and click on one of these objects here, and I think I'll go ahead and do it on this one here, if I can. I'll find my cursor. This is a Newtonian plot of the elastic collision. We're going to do this one first. Oops, that didn't happen too well. I've got to make sure I get the little finger showing there. So this is a Newtonian plot on the right of space versus time, which you're used to in calculus classes, right? And then on the other side, it's space versus space, basically. But we're only confining this thing to a line, so we don't use the y region at all. Now let me go back here. And this is the thing about these animations. They don't occur on the slides that you have. The slide takes you to the browser to show the movie. Someday we'll have that. Now here's another view of that same collision, but in Minkowski plots. Minkowski puts the time axis vertically. This is Einstein's math teacher that did this. Okay, in order to do relativity and to do what will be the last construction in this class was what's on this board right here, on the back of your textbook as well. Okay, this is where we really explain how quantum mechanics and relativity are the same subject and work together. Relativity is almost always done in a space this way, time that way. And of course the space this way has 3 dimensions, times the 4th. Okay, that aside, let's go ahead here to look, first of all, what's the conventional solution that you would get in almost every other mechanics class beginning with high school and going right on through. Basically, you look up the usual momentum and energy formulations and axioms and solve them together. Okay, you've probably all done this a number of times. We're going to do it differently. what we're going to do is just use one axiom. Well, really 1.5, as you'll see. Okay? But the one axiom is that all masses and masses keeps total momentum until it's changed by something outside. Doesn't sound like you're saying much there. But that is all we're going to use. And that's the idea of using critical thinking and logic in a powerful way, is to say the least, and I'm going to make that point a number of times here before we get too far. So, here we are going to state that very clearly. I want to put it on all screens just to make sure that it is clearly available from wherever you're sitting. The idea is that the velocity of these two objects changes violently, quickly, but not the total momentum. And this unconventional way that we're doing this, we're just basically going to draw two lines on the graph paper that you're there, and we'll be almost done with what we do today. But there's a lot to say around that. So, the idea that that axiom, first of all, is the change occurs rapidly. Yeah, boom, if it's a highway collision, and clunk if you're not. I've got some sound effects here for this. I'm imagining the perfectly elastic condition, the sound would be a boom, okay? Whereas this one's going to be a crunch, or something loud. In any case, the idea that is behind this is just the geometry of what goes on to yield the results, whatever that happens during that collision. So I want to make sure that this axiom that we're using here is cleared in, this is the philosophy part of this class right here. And I can probably go ahead on this one as well. That's the Latin, but translated means don't make pluralities of conjectures without necessity. The idea is keep it simple. Assume less to prove more. The less you assume, the more likely you are to make progress. And if you're doing coding, all of the coding that makes up all the things that we've done both for research and teaching, keep it simple, make it powerful. So that's Occam's razor. Okay, that's a lesson in philosophy just in a few minutes here. So what we have here to do, what it is that we need to accomplish in order to get this, is to take that axiom seriously. So the idea is that before, that is, input to this thing, V in of the VW and the SUV, they sum up with the weights, their mass. They sum up, you give a number that is the same before and after and during this collision. That's the thing that's really quite remarkable about this conservation. Now, the thing you might ask is, does this axiom have anything to do if we were doing a class in quantum mechanics? Do you ever see an axiom like this in quantum mechanics? No, you don't. And we'll see why that is. But for classical mechanics, this is really where it starts. So, basically here are the numbers. We get 60 miles an hour here, we get 10 miles an hour here. We're not using MKS, I'm going to take an English units for a while here. And then we want to find out what's the final velocity of the SUV and the final velocity of the VW. Those are two numbers that could be put in there. But whatever those numbers are, they better add up to 250, which is the constant that's the sum of these two. So that's what we stand here. That's the problem we need to solve using the best logic that we have available. Okay? So those particular equations, the equations that I've just written there, really simple Cartesian equations, Cartesian coordinates really, x and y, but we're looking for velocities, so that's a little different from what you're used to perhaps. But there's Mr. Descartes, who's the inventor of coordinate systems, that, as far as we can tell, one of them anyway. And this guy here goes much earlier, talking about 1300s, for William of Ockham, who walked all over Europe, going to different monasteries and learning things. It's amazing to think about some of the history that's responsible for us living in a room full of computers and air conditioning. So the things that have happened to make this. So here is how we're going to actually do this problem on a piece of graph paper. The piece of graph paper that you have is already marked off like this one here. So the first thing that we're going to do is label it. Make sure that you have a label on that thing that indicates this is the velocity of the SUV, the heavier of the two vehicles, and then the VW is up this axis right here with 10, 20, 30 miles per hour, just like this. Now the starting point for this is, as we've already stated, the input for this is that this guy is going 60 miles an hour. And this guy here is just putzing along here at 10 miles an hour. So the initial point on this velocity graph is located at 60 for the SUV and at 10 for the VW. So right here is a point that represents a vector made of components for different objects. That's a little strange, but that's the way we're going to do it here. And this is the the velocity in here. So I'll just write a letter I in at the beginning of that. And then what we're going to try to do is figure out where we're going to wind up. Okay, somewhere along the line that conserves momentum. Now it's pretty easy to figure out where that's going to be. That it's going to be at such a line that has a slope that is the ratio of the masses. If this is going to be a constant, I go ahead and divide through by the VW here to get the mass off of it. Then I can get the velocity of the VW, solve for that using this. Now here I put a minus sign there because to go over the other side of the equation. And then the total momentum right here divided by that number. That's what we're dealing with. This right here with the mass of VW, and don't forget at all times here the mass of VW is 1 unit, whatever unit. We're not being careful about MKS units here. Say 1 ton, and the SUV is 4 tons. Okay. Both of them are smaller than the actual vehicles that are, I think they're more than 4 tons. Volkswagen's more than 1 ton. But in any case, that's the thing that we're trying to solve. And the slope that we're talking about here, slope minus 4, basically, what's going to happen is I change the velocity of the SUV by 1 square here. I'm going to change the velocity of the Volkswagen by 1, 2, 3, 4. So that's what you do on your graph, is you simply count over 1 and then count up 1, 2, 3, 4 and put a dot. Okay, so we're going to maybe pass through that dot in the middle of our collision. Then we do it again here. You go 1 unit over, and again, that's negative, and then go positive 1, 2, 3, 4, another dot. Okay, and by this time you should be pretty close to the top of the graph in the first quadrant of the graph paper that you have. Now, what I'm going to do is I'm going to borrow a magnetic ruler here, and I'm just going to plunk it right on top of this thing, because you see when I put a ruler down on the blackboard, unless it has a magnet, it's going to fall off. So I'm just going to put this ruler where you should put yours to make sure that all three of these dots are on the same line, Okay? And so the answer to our problem will lie somewhere along these lines here. So I'm going to go ahead and draw that line carefully. Now we just hope it isn't way up here off the paper or graph, and also doesn't come out backwards. It could, this points down here, we'll talk about those later on. But basically somewhere in this neighborhood we can expect the solution to this problem. That is the final velocity of both of the objects. Okay? All right, so the first problem that we're doing here is the crunch, the inelastic collision. And the question is, where would that one be? This one we can get just by thinking carefully. Okay? And maybe I pause for a minute. Where would you expect that solution to be? This is critical thinking now. Where would you expect on this line right here to find a solution for our crunch collision, where they become one object? Okay? So imagine the answer to this problem is worth $1 million. Okay? And someday you're going to be working on a research project where the answer to something is worth $1 million. That's getting to be common these days. Okay? I'm not going to pay you $1 million for this one, but still, it's the exercise of those cells in the cranium that is worthwhile in making this. Now, don't be timid. If you think you know the answer, please tell me. And speak up at any questions you have about this before we get to the answer. Now, I'm going to draw the answer here in red, but you should kick yourself for not seeing where that answer is on this line. Well, what do you have when these things become a single piece of metal, right? These two vehicles. You got one mass, right? Velocity is equal, right?
Special like that.
Go ahead and say what you were going to say.
Both of them change the velocity becomes 1, so
The velocity becomes equal, right? So what we got to do is draw velocity equal line,
50, 50.
right?
See? I heard some clicks.
Right. You're on the right track, and that's go pick up your $1 million. There's the line that they will have to be on because they have become one object. Right? So I'm going to have you draw that line for all sorts of reasons, but mainly because we've got one object that has coalesced out of the two. Okay? We don't have to go any further than that for today. Okay? So there's the answer right there. They both are going to be going 50 miles an hour. Okay? Not so hard, right? I mean, when you see the thing, oh, of course, right? But that's the way all of these things are. That's Planck's law, of course. It always comes out, of course. Well, we still got work to do because we want to do the elastic collision, the one that would occur in a parking lot if it was, instead of miles per hour, it was feet per minute. Okay, they're just barely moving, right? That's the other part of this thing. We need a realistic result. So basically, we're insurance agents now. We're looking at an anatomy of a collision and we've been called for a parking lot now, okay? Somebody had a collision in a parking lot. No damage, it's elastic, at least no damage you could see. It's elastic. What's elastic mean? If you heard anything, then it wasn't a perfectly elastic collision because some energy came over. That we're going to talk about later. In any case, what do we do to get the answer to that? Okay, this is a little tricky. Okay? I'm stopping the thing right here and asking the question, what is the final for the elastic kabong collision that we're going to be imagining here. Okay, we've got the inelastic collision already solved. Okay, that's this. Okay. Right here. Okay. So that we have just done. Right? Big deal, but clearly the other answer is somewhere else on this line. If we've got that axiom, we can't change that. We've got to work that. So this is the big deal right here. Okay? And that's the trick. Now you use your compass. This is what we're going to spend the rest of the class talking about. Why is this true? This is really an important piece of symmetry that's going on here. Okay? So now I got to find my compass without tripping over the wires and pulling everything off the table.
Stupid piece.
This particular point right here is really important. This is a vector we'll call the center of momentum vector. This, thinking of it as a vector, okay, this is VCOM. Now, I'm going to write it as a vector, fat letter, little arrow over it. But that's the key one. And in honor of that, we put the compass point right on there and put the drawing part of the compass, the pencil, right down here. And this is hard on the blackboard, but it should be pretty easy for you to do. First of all, I have to make sure that my little needle doesn't slip up there. I'm going to draw the entire half circle. It comes up here and hits the line right there. It happens to be another point that we use to get the line, but that is the answer there. There is, if this is down here, velocity initial, input, this guy up here at the top is going to be the final velocity. We'll just call it vector velocity final, F-I-N, fin. So we've got N, we've got COM, and we've got fin. Those are the 3 points that are important for this particular collision and the geometry thereof. So, okay. Well, end of class. That's our solution today. Right? But we got to talk about it. There's a whole bunch of stuff behind this. Okay? Symmetry behind this. What's going on with this? Okay? So, I'll advance this guy to that point, and this guy, and this guy. Okay? Now, stop me if there's anything here that isn't clear. Okay? So what you'll learn is by asking questions. And when you're in the group meeting for your research, you better be asking questions all the time. You don't know what the hell's going on, right? Okay, so this is sort of a picture of the thing, and it's a picture which shows them as vectors. So that doesn't hurt to go ahead and draw some of those lines. let's start with the initial velocity vector. And be aware, this is weird because you've probably drawn lots of vectors in your calculus or early mathematics classes in which you had arrows that signified something. Well, this one's kind of weird because this is the not X and Y, this is vehicle SUV and vehicle VW, right? It's different particles. Okay, that's what our space is. It's particle space or something. It's got a weird name. And that's the thing, when you teach this, you have to point that out probably very carefully. Anyway, here's the other one. Here's the other velocity vector. Okay? And out of these two vectors, we make a parallelogram. This is just two of the sides for that. So there's the vector v fin right there. This is the vector v in down here. Now with your compass you can go ahead and finish this in order to make the drawing that's shown on the slide here. And I'll go ahead and advance this one as well. Okay. So we're going to go ahead and catalog these things and describe them. There's another name for these particular vectors. It's called the weighted average. So let me get that up there as well, just to keep us in sync here. That's what we're actually calculating. That's interesting, something to know. But basically what I would do, have you do, is be ready to calculate or to draw a parallelogram. And what I'm going to do here is I'm going to, first of all, set this compass here, and this is going to be a stretch. Okay, it's about as much as my compass would do, but I don't think you'll have any trouble getting this with the compasses that are that you have in your hand. Here I draw an arc through that point, and then I take it over and draw that arc again over here. Okay, now I make a nice generous arc so I have all the chance in the world to capture the other side of the parallelogram, which is made with this vector. Okay, so here I take my compass and strike that one off, and we're doing 6,000-year-old geometry here. This is what Thales did. He's famous for this. What did he do, though, with that knowledge? He lived in Turkey, he went to Egypt, and he figured out how to map where your farm was after this Nile River had flooded it. They did it every year. So figuring out where your farm was had to be done on paper, and he used ruler and compass to do that. That's the start of civilization. These guys, okay, 6,000 years BCE. That's 6,000 years before Christ, but it's called before Common Era. That's what BCE stands for. Okay, so where those two lines intersect is the rest of our story, which is this parallelogram. Now these are all things I'm asking you to do on your homework for this week. So we're doing a good portion of the homework in class here today. And here is the other vector that we call Vn. Now it's shown up on the top part of this parallelogram. Okay? And that's stuff that we'll use those lines for other things shortly here. But in any case, that's pretty much all the geometry we have to do today. And it involves straight lines. Okay? All right. What else here? Let's do some algebra. This is back and forth between geometry and algebra. This is the way I think that very powerful way to make your mind go further. So what I'm telling you here is, first of all, that this velocity this velocity is a vector at the COM, and the actual magnitude of that VCOM, okay, is a weighted average, literally weighted by the mass of these two vehicles. V1, this guy, with M1, 4, and then M2, the pokey VW down there, that has only a mass of 1 ton. Okay, that's going to be a 1 right there, and a 4 right there, weighted 1 to 4, and then divided by their total, 5, 1 plus 4. Okay? And the thing that's interesting about this, that's a physical interest, is that all during that violent collision, where he's sitting here, sitting here, sitting here, and then bang, he's up here. All during that collision, this number and this number are the same. Any point on that line is going to have the same outputs. Well, that's worth noting. That's kind of a cool thing right there. Okay? This makes you say that. Okay? All right. So, weighted average of these two velocities, 4 to 1 weighted. Okay? 50. That's our VCOM. Remember that we got very first. Okay. Any questions about that? Make sense? All right. Now, at this point, I want to make sure that everyone in this class is really good at dealing with vectors, both in the usual notation that we're going to see here, that is, with this. And I do point out against these XY components, pretty weird because they're particle 1 and particle 2, SUV and VW. That's a little bit weird. Configuration coordinates, sometimes they're called, or whatever. Okay? And you are probably used to giving coordinates like X and Y. And you're probably not used to, maybe, unless you're doing your quantum mechanics, used to writing them as a row and a funny little bra vector. Okay? And then this guy down here, I'm writing that one as a ket vector. Okay? You guys have all been playing with those vectors, right? In your first quantum mechanics class. It used to be that we had to have a whole class on just dealing with Dirac notation. But pretty much everybody learns that right off the bat. Well, we're going to learn it here for our purposes as well and make use of it. This is the way we keep track of things in this business. So let me go ahead on this thing here to get these up where you can see them. And I'll get this one too. Probably don't have to do that one because it's harder to see, but I'll get these 3 going from now on. Okay? So basically what I'm interested in here is the scalar product. That's this 4090 vector that we have up here, if it were turned on its side, times the 6010 vector that we started with, the in versus the fin, the product of that two. This is Dirac's notation for that. There's the actual magnitude of it right there. For what it's worth, that scalar product comes out to be 3,300. And we're going to, play with that sort of thing. Now here's something else that you should be familiar with right now. In addition to a dot or scalar product, tensor products are also, or outer products, are also extremely useful. Standard notation, and I want to make sure that this little circle cross here is something you're sort of familiar with. How many people have some familiarity with this little guy here? Okay, there's a high school student who has some familiarity with it. How about the rest of you?
I've seen it.
Seen it, but not really gotten friendly with it, right? Well, it's something you definitely want to get friendly with because it's going to be the first thing that happens in quantum mechanics. Okay? And this is the way they're going to do it. Instead of putting it in the dot product like that one where you take the two vectors and slam their flat sides together, you turn it to the points of length, and that makes a matrix. okay? So I go 60 times 40 and write it down, I don't add it to anything. Then I go 60 times 90. Then I go 10 times 40, and then I go 10 times 90, and I get a matrix. That's the outer product. The Cartesian product is another name for it. Descartes apparently had this concept already up and going in the 1700s. All right? So, the column vector, or ket, is on one side. In this case, as opposed to that one, it's on the left side. There it's on the right side, where it's making a number by summing. Okay, so contrast these two products. Okay, they're very, very different. Scalar versus tensor of vectors. That's kind of the bookkeeping that we use for, and as I say, we're going to use the same bookkeeping whenever possible that you use in quantum mechanics, just to get used to it. Also, it's very powerful. They have to be a little bit cautious with it, and that I'll come to in just a minute here. But there's something else that you have to be cautious with, and that is idealization. In order to make progress in physics, we often have to assume things that aren't quite true. In fact, we almost always have to do that, because we just don't know everything. We will always be doing this idealization of models, okay? And our idealization here is no rolling friction, no air resistance, all of the background is just gone. These two things are just doing their thing in space, if you like, empty space. And also, I'm cutting down the dimensions that are really existent. I have to mention those just to tell you what's coming in this textbook, in this course. That I will go ahead and do right here and here. Leave the pictures up just for the heck of it, for the simple stuff. But you realize, of course, that these two variables can translate in 3 dimensions, not just along the road. Yeah, they'll be moving along the road in our special thing here. But we've got 6 degrees of freedom. That's the name that's given to dimensions in both classical and quantum physics. Okay, so we've got 6 of those. We're not done yet. These guys can turn, roll over, rotate. If we're in space, they would be at any orientation possible. We've got 3 rotational dimensions for each, or 6 altogether. 6 more degrees of freedom. Now we won't be doing these guys until about Unit 4, but really Unit 7 is almost the end of the course before we get going with these things. This is the object that we'll use, this machine right here, the Euler angle machine, in order to understand those degrees of freedom. So that's coming. And then, each of these objects is made up of thousands of atoms and molecules, and there are modes of vibration for every object that has more than one particle, whatever a particle is, composing it. So we've got n atom molecule, whatever, and huge number for vehicles. It's already a large number for any of the molecules that you work with that build up solids. So just be aware that all of these caveats are coming. And it's, once again, units 3 to 8 where we get to play with that in some details. Okay, now let's go back to our simple situation that we have with 2 particles each going in along a single direction. Okay. And this is where I want to make sure that you understand a Galilean translation. It's a symmetry transformation, and I can hardly do any physics at all without mentioning symmetry. It's my favorite stuff, but it's nature's favorite stuff too. So I don't feel bad about selling it to you here. And let's get up to that point right here as well. What you can do, you see, in space, and I'm talking about this space where we have a SUV versus VW, but all 3 dimensions of this and all 3 dimensions of this, is simply translate that Galilean transformation to the center of this particular collision. That's an interesting thing to talk about. And the idea, of course, is that if you increase your velocity, if I sitting here and I feel that you guys are lazy because you're not moving, like you're sitting down, you can't move you can't translate very well. But if I want you to translate, I can arrange it very easily. I can start walking at 3 miles an hour across the room, and this whole class is moving 3 miles an hour. We're in my frame, right? Okay, so no problem getting you guys moving, right? Now you're going the other way, 2 or 3 miles an hour, okay? That's an important idea. Okay, the idea, the rest of the world appears 50 miles an hour slower. Galileo thought this was an interesting way to state the relative velocity. Now, the smartass would say, sir, does that include a light wave or pulse? And the answer is, yeah, kinda. But you probably have already heard that one of the things that happens when I walk across this room is that any light pulse that I could possibly see has not changed by 3 miles an hour, or any change. It's done nothing. It's still the same speed no matter how fast I go across the room. That's the beginning of relativity right there, the special relativity. Okay. But this is a long time before this guy would get to do that. Died before we even got close to 1905. All right? But give him credit. It's true. Yeah, kinda, because they thought velocity of light was infinite. So when you add your 50 miles an hour to infinity, no change. No observable change. Observable being the key word here. Okay? All right, when we get to Unit 8, we're going to be talking about that. And this diagram here is entirely based on having velocity of light. That's the axiom of both relativity and quantum mechanics, is that all colors go the same speed. Okay.
I've seen one.
Now, each time you pick a new frame, like the COM, you're simply subtracting 50 from both of the dimensions. So that means you come down the 45-degree line. You do all your translations. Everything moves along the 45-degree line if you want to change reference frames in classical mechanics. Okay? So here are all of the other pictures of the VW versus the SUV in different frames, including this one right here. And that's a very special one. That's a very special frame for this problem that we're doing here, involving these two protagonists, the VW and the SUV. Okay? So when we get here, it's pretty simple what happens. They both have the same velocities, plus or minus, and they just kind of switch. And they come back to these points in an elastic collision. If it's inelastic, they just go there. Really simple, right? Hardly need any geometry at all to do that one. But that's a special symmetry point for this particular problem. Key way to think about it. Okay? Now, what's interesting about this thing is that a lot of these, there's some special frames here for the VW. This is where the VW is viewing its frame, and of course it's not moving in its frame. And then there's this one right here where the SUV says, that's my frame, initially anyway, and I'm not moving in my frame. So that was the case where the VW's velocity is 0. This is the case right here where the SUV's velocity is 0. This is the case here where the VW's velocity is 0. Okay? And then later on, you'll see the same thing happening kind of in reverse over here. Here's the SUV with some velocity, but the VW is 0. And then anytime one of these things crosses an axis, that's a special frame. These guys are just, I just sort of drew them in to be, this one's special, but that one's not. Now what's interesting is that there are time reversal pairs for this one here okay, is a time reversed version of this one, and this one to that one, and so forth. You just draw a line through the origin from the two things, and you get a case of time reversal. Flipping time to minus time, that is, running a movie backwards. So, if you flip a velocity, okay, this very special case here, that is pretty neat. You use the same numbers for initial and final. Okay, so that's, I guess, as much as I'm going to say about the symmetry. And the center momentum is this sort of the nexus of this symmetry. Okay, now let's do the vector algebra of the collisions and get going here with something besides momentum. There's something more to this, and this is the this is where this making classical mechanics simple really shows itself. So first of all, let me point out that if I do a matrix, and that's going to be a mass matrix with mass here, usually 0 here and there. I operate on that. I turn velocity into momentum, the product of the mass and the velocity. So this is a pretty simple diagram of a matrix acting on a vector. Dirac notation, I say, or Dirac would say, is much simpler, but it's not really that simple, because if you use it fully to indicate the component x, x, and x, y, and y, x, and y, y, I just use different letters for that. This looks simpler than that, but this is what is showing everything that's going on. And then there's the result, which is this. Okay, so be aware that you get writer's cramp when you use Dirac notation, but you keep track of everything, and that's an advantage. So it's worth the extra time, perhaps. Okay, so this thing, this matrix right here, best name for it is Inertia Tensor. Now, where would this thing come up in a mechanics class other than ones given in this room? The inertia tensor comes up with rotations. Okay? We won't be getting there for a while. But it sure comes up here. And it's only 2 by 2 here. Okay? This off-diagonal component of the mass tensor is 0 for us. Okay? But almost everybody in this room is going to end up working with things in solids. And in solids, the mass tensor is not usually diagonal. So it's a good chance to get used to that situation. And the 45-degree diagonal for this, that kind of here, but the whole idea is that there are 3 ways to write the total momentum, which we've gotten by taking this denominator of the weighted sum and putting it up in front of the velocities, multiplying the velocities in this for this diagram here. This being the initial, this being the final, this being halfway, the COM. Okay, all of those sums are equal here, and they're equal to the total mass times the velocity of the center momentum. This is regardless of whether it's an elastic or inelastic collision. This is good for everything. So we want to make use of that. We want to see that, and we want to see it using the matrix algebra, vector algebra. Okay, is there anything I'm leaving off here? Points of vectors. These, and these all lie on that line. Okay, that, as I said, that's quite a bit of magic right there in that axiom. The one axiom that we have for this huge subject called classical mechanics. Okay, so now we get a little bit hairy. Now we're going to go ahead and write these things out using the tensor notation. So here is this equation. Punch this one up to get that, get to that point. here we are, okay, again, with off diagonal 0, but everything we do here is going to work when it's not 0. So use something you can take to be useful in the waves that occur in solids. But writing a thing as a quadratic form is really key to this. So this will be our first look at something we'll use throughout the course, and that's the quadratic form, in which two vectors give a number, and involved in that is a matrix, which for us is diagonal, but later on not necessarily so. So these are the numerical details that go with this. So what we have here is the VCOM, remember that's 50 miles an hour, so that number here, and then the total momentum, this is a number as well, but so are all of these. All of these are scalar products involving a matrix in the center, a ket and a bra. Ket and bra, okay? This is the initial velocity. This is the COM velocity. This is also COM velocity. Here's the final, 40, 90. I didn't really pause for a moment here and point out what a disaster this is for the VW, right? He was going 10 miles an hour, minding his own business and looking at the road, I presume. But maybe he was smoking marijuana, who knows? The guy down here that was going 60 miles an hour has only lost 20 miles an hour. He's just gone down to 40, right? This guy's gone up to 90. It's not survivable. Very likely unsurvivable. Okay. Now the thing about cars now is they're designed to crumple. They're really designed to waste. We're going to be talking about very shortly here energy. So this guy, this thing right here, 50 miles an hour. If the crunch occurs, it is survivable. Okay, let's see if there's anything else I need to say here. Let's get all this algebra and some more up on the screens here. I go ahead and do it on the last one here as well, just to keep us in sync here. Okay, numerical details involving the matrices. So this matrix times that matrix gives me something that's pretty simple. Now it's really just a dot product of two vectors. Okay, this vector COM dotted this one, where that's become sort of a momentum. This is a mass times the velocity, mass times the velocity. So there's a momentum quantities. There's a name for the product of velocity and momentum. And that's something, that's a quantity that you probably haven't played with much. We should have, because it's really key to quantum mechanics. But this is called action. The product of velocity and momentum is a form of action. So that's something we're going to spend a lot of time with before we're even out of the review unit that you're looking at now. In any case, we've got 50 times 250 units of action here. We've got 12,500 units of action, whatever the units are. We haven't been careful with units yet, but just to keep things simple, we're doing tons and miles and hours as our instead of MKS. Okay. This guy comes down to that, this guy comes down to that. Okay, so we get here 50 times 240 and 50 times 10 added up. This one right here. These had better be equal. These all better equal 12,500, and indeed they do. Okay, so that's what we're talking about as far as the action units. But what I want to show you is where energy comes in. The energy is something you claim to be more familiar with. So let's get to that. There are if I separate this sum here, and remember, this particular sum, that is the v fin vector, that's this guy here, plus this vector, divided by 2 is this guy, right? That's the key thing. So that's what we're actually making here, that VCOM vector sitting right there, but written in terms of initial and final. Okay? And multiplying this thing with the initial, multiplying this thing with the final, is supposed to be equal. And then the whole thing is supposed to be equal to that, VCOM dot VCOM. Okay. So I separated them out. So here I have something that's really of interest to us. That is the kinetic energy initially, and that's the kinetic energy finally. But then we've got this weird lopsided sign. It has the fin dot m dot n, initial and final, on either side. And then we've got the same thing over here, except now the initial's on the left side and the final's on the right side. Call that the lopsided sum. Okay? And let's see, that one there as well. Here is the matrix deal that this thing has. The numerical actual numbers that come out of this are shown here. Excuse me. And the idea is that this thing right here is equal to this thing right here if the M matrix, that's this tensor right here, is symmetric. And boy is it symmetric. It's two zeros equal to each other. But it will still be symmetric in the stuff that you do in solid state physics, where you're talking mechanics of things bouncing around in crystals. So that's cool. The transpose symmetry of that matrix makes the lopsided, this guy, equal to this guy. And that leaves you with 1/2 mv squared, roughly speaking, equal initially and finally. So we do not treat the conservation of energy as an axiom. We're proving it here for this problem. Okay, that's the power of critical thinking, is it's not an axiom in this business. Okay, so you end up here with them being equal because they're symmetric, but then that is the thing that lets you give the kinetic energy relationship. So this is the fin in term subtracted because they were equal due to symmetry, and you're left with the kinetic energy initially being kinetic energy finally. Now, how did this come about? What was required to do that? That's a very special case. And what it's assuming is that the collision, which had a low point right here, rebounded perfectly to make the final velocity. So they came in, but they didn't crunch, they just sort of put some potential energy in, and then we got it all back again perfectly to here. Time reversal symmetry is what we've got if we make it from there to there. If we make it short because we wasted some energy, we'll be somewhere along this line here afterwards. That will not be a conservation. But this is. This and this have the same kinetic energy. But all along this line where momentum was the same, total momentum, total energy is not. It drops to a low point here, and then if you're lucky and the time reversal symmetry holds, it makes it back to here. And that's conservation of energy theorem, subject to time reversal axiom. Very important that time reversal be there. Okay, and that's essentially the lecture today, but there's some more details I'd like you to look at that will help you with the problems that I've just given you. And you should all have a copy of that with lots of graph paper. And there's more graph paper up here if you want to get extra copies of that, or you can get it off of the web. Okay, so here is that statement, and there is the kinetic energy numerically displayed, and that I'm going to have to get.
Boss, I don't have any water, but here's coffee.
I had better not.
Yeah, that's kind
that'll
of right.
do me in.
Sit here for a while.
I had a heart valve replaced, and so it screws up your, well, it screws up a lot of things. Anyway, this is the equality. We're talking about 7,250 units, whatever those units are, of kinetic energy being preserved perfectly if we have time reversal symmetry. So that's the main idea here. Now, how do you geometricize the geometry? I mean the energy, kinetic energy. How do you get that in a geometric form? You see, so here are the vectors all again. Here's these equations written out the way we did in terms of just simple algebra. And when you look at this and go ahead and get the kinetic energy on the denominator of the horizon, this is in or fin, assuming that we are time reversal perfect. We're keeping that before and after fin and in. So I divide through here by the kinetic energy, and then make it a square of a square root. What you recognize immediately if you've watched your high school geometry teacher show you an ellipse, what we've got is an ellipse here. We stay on the line, but that line hits the ellipse at 2 points if the energy is conserved. So there's the geometry right here. So the idea is I'm going to be asking you to draw an ellipse in a couple of situations for collisions that completes this discussion of a geometrical approach to the axioms of collision quantum mechanics. So that's an important key piece of this whole story right there. Now, if we had not done it perfectly here, and you calculate the elliptic radii, A and B, major axis, minor axis, it turns out this is the minor axis and that's the major axis, so the A and B are flipped. Sorry about that, but that doesn't really change anything essential to this discussion here. But one of the things you should notice about these numbers when you get them is to check them with the geometry. In other words, you're going to be able to do this algebraically, obviously, but look at this. This is really close to 60. Okay, we started out at 60 miles an hour, okay, and we went up here to something less than that, 40 miles an hour, okay, but when you're talking about the actual coordinates of the ellipse, that is the axis right here, okay, and the axis right here, where does that ellipse come through? And you probably can't see it, but it's a few pixels off of the 60. Okay, it's 60.21. All right, and then the other thing, this is 120 plus 0.42. Okay, so that's what that's the thing that makes this a little persnickety. That is that you have to be careful with your drawing if you're and ellipses. I'm going to show you how to draw ellipses fairly quickly in a Cartesian form in just a minute here, but that's something that's going to come up in these problems. Okay, you're going to have to go through this and get used to it. Okay, now we're got about 10 minutes left here. I'd like to show you a couple of things that we're going to be talking about next time, and this is where you go ahead and make a collision, okay, but then you let that collision get sent back. You put some bumpers at the ends of the tracks where these cars are, so they bounce off. Okay, so this is a picture that so here's two masses. The SUV and the VW are now M1 and M2 in a movie that we'll show in just a minute here. So let me just go ahead and get that going. I'll probably better to do it in the center screen, and then we can mess with it on the side screen here in just a minute here. Let's see if there's anything else that I need to say before I do that, though. These are points that have come up in your problems when you work with these vectors and ask, you know, what happens if I got stuck at the VCOM? That is, if it did a crunch and the Volkswagen guy got to live, we would have a picture like that. And I'll go ahead and put it up here so I can point at it from where I'm standing. These velocities aren't too different, so the ellipse is not all that different. It's very close to the other. So this is the energy that you'll end up with if you have a perfectly inelastic collision. And it's the energy that you would have, kinetically speaking, if it was a perfect collision, because you would pause here with that much potential energy lost. There would be that much energy that was in potential energy and would supposedly give it all back getting to that point. That is, you know, just part of what we imagine is going on in a mechanics collision like we're seeing here. Okay, so all of the numerical results here that are kind of neat, that show you what the potential energy is. I used to give this as a problem, and very few people would solve it. But this one is this thing that actually tells you what that potential energy is. That's a compression that occurred and caused that to happen. And the other thing that's interesting about all of this is that in the center of momentum thing, this problem is trivial. So you might have wanted to go there first, get that ellipse, and then you can draw a line along there in which all of the other collisions will reside, because everything translates along the 45-degree line. And this 45-degree line has to be tangent exactly at the point where the velocity reaches. These are little intricacies of geometry that are just beautiful. I mean, I find this stuff really pretty when you can look at it and graph it. And of course, computers let you do this easily. Little computers you have that are 6,000 years old that you're using right now are not as elegant as the Macintosh or whatever. Okay, so these things, key axiom of mechanics leads to conservation energy theorem, if and only if there's T-symmetry. So that, if you could sum up this whole lecture right now, that would be the result that I would be selling you. There's another way to plot it so that you can see all the pieces coming together in their little tangents here. Now, be aware, once again, we talked about idealization. As usual in physics, opposite extremes are easier to analyze than the generic real world between. Okay, so here we have our perfectly elastic thing, and then we have the other extreme where it all ends up at the COM. Here's some, this is a kabong, this is crunch, this is just ka-wump. So I go ka-wump and end up here. Now there's something called the flump that we haven't talked about, but you could end up there too. And we'll have to figure out how that happens later on. But this is obvious. That's the first thing we did, is calculate that. Then we used the compass to get this one. So we jumped through the real world in between, right? And that's the way physics is. You'll have these nice extreme cases where some symmetry principles work, and you can write things out analytically. Oh, that's so beautiful. Then really it gets nasty in between there. But that's what we have computers for. we don't have to really mourn this. You can read this political message at your own time. Okay. In any case, this is T-symmetry at its best. This is T-symmetry quite a bit reduced. And this is T-symmetry at its least. There's no T-symmetry. Completely lost it. All right. Okay. Now, before we get out of here, I want to make sure that you see this particular page in the of Unit 1. This is Chapter 1. Okay. And this is a simple way to draw an ellipse. If you know what A and B are, okay, it's really quite easy. You draw a circle for B, you draw a circle for A, and then you just pick whatever angle you want to put a point down for, and you run your thing across the graph line here, see where a graph line from that point intersects a graph line for that. That's a point on the ellipse. Okay, that's a lot easier than sticking thumbtacks in, getting string, and drawing an ellipse using polar coordinates. This is Cartesian construction. This is Thales. This is 600 BC. Okay? So, be aware of it. All right? It really helps when you're doing these problems. Okay, once again, the various things that went into what we talked about today, and the ellipse that we talked about. That's the graph paper I gave you. What I'm going to do now is go back to what we'll be talking about next time, and that is when these collisions keep happening. So I'm going to take this one back to here, and let me see if I can find, there's a link hiding somewhere on this, and there it is, I think. I will take this one back as well. And I will go ahead and click on this guy right here that shows what's going on. This is, there we go. Okay, so here comes SUV going 60 miles an hour, and there's the VW putzing along there at 10 miles an hour. There's the point over on the right-hand side in velocity space. Bang! It changes to the final velocity. Okay? Well, that's cool. There's the computer solving a differential equation for motion and forces and all that kind of stuff that we haven't really talked that much about. But in any case, when you want to resume this, and this is true of all the animations that are there, usually they stop at some key point, and this is where the thing is going to reflect off the ceiling. Boom. Okay? And there's a line indicating that reflection, and there's another collision. Okay? So we'll just stop with this. We're almost out of time. But it's worth watching this thing. It's really kind of cool. Because what we're doing is we're just considering all the possible collisions that would occur if there was no loss of kinetic energy. Time reversal for everything. And you can change this program so it's not and see what that does. That's interesting too. But now we're coming to a really big head-on collision. Kabam! And we go back up there and put a point down that's symmetrically displaced from the one that was already there. And then we go through that again.
This is a vicious one
Okay?
here.
And you probably noticed that all the points where they're not engaged with either themselves or the floor or the ceiling lie on the kinetic energy ellipse. So this would be a numerical way to discover the kinetic energy ellipse. You just do a whole bunch of points, and every one of them is on the ellipse. This ellipse that is not drawn here, but we've been drawing. Okay, and then what's cool, particularly cool about this particular example, here they're almost zero for the SUV, and he gets hit again, and then he comes back, and boy, they're they're very close to the same speed, only a little bit off. So this is a near symmetry. going on just between these two guys because they have mass 4 and 1. Kind of weird, huh? Who would have thought that bouncing things together would start to get interesting? Well, we have a lot to do with it. And one of the first jobs is to get rid of that damn ellipse and replace it with a circle. Took me a long time to discover that, but I realized, my gosh, I had a hard time making an ellipse. It's like, if I just have to draw a circle, I'd be way ahead. And sure enough, you are. We'll talk about that next class. Okay, but meantime, do the homework. It's due a week from now.
Are you all aware of the website that's available to you?
Yeah, these are
Yeah.
things that we
If
should
you're
be aware of.
Check your mail. There should be a link to it, and virtually everything will be available to you electronically as well. Your textbook will be electronic, so you can carry it around on your pad.
Yeah,
And
you don't have
homework's
to bring
already
this
posted?
notebook every time. Although it's a good place to keep things that you do, homework and stuff like that. The main thing I think that's important is that all of the lectures are there too. So
Everything.
we
The solution.
We usually get that up a few hours before the class. And then last class will be a video on YouTube that TC can get up fairly quickly. Well, assuming we have one in the camera right now. Okay?
Yeah, in case you have to miss.
Well, it's going to be a fun year. This is probably different from any course you've taken so far. In some ways good, and maybe some ways not so good. But we're trying. Okay, we'll see you on Wednesday, same time, same station.